Hello. In this video, we're going to take a look at the RL dipoles and how they generate current. The RL dipole consists of an ohmic conductor of resistance R, connected in series with a coil of inductance L and resistance R. Consider the following electrical circuit. The diode is used to prevent sparking at the terminals of the switch when it is opened. When the diode, which is assumed to be ideal, is on, it behaves like a closed switch. It behaves like a closed switch. When the diode is blocked, it behaves like an open switch. We start by establishing the current. At time t equals 0, the switch is closed. There is a delay in establishing the voltage across the resistor and therefore a delay in establishing the current in the circuit. This is due to the presence of the coil. The oscilloscope now shows the voltage across the resistor, that is, you are on channel 2, and the voltage across the generator on channel 1. For example, here we have a coil with a small internal resistance R equals 12 ohms, and an inductance L equal to 1 Henry. A generator terminal voltage of 6 volts and resistor resistance equal to 100 ohms. There is a transient regime in which I increases until it reaches a constant value, I max. We have then reached the steady state, where I remains constant equal to I max. By applying the law of additivity of voltages, we have UR plus UL equals E, and replacing UR and UL as a function of I gives E equals R total X I plus L di over dt. Divide by a total and you get E on RT equals I plus L on RT X di on dt. This is the differential equation verified by I, T, when the current is established. The general solution to the above differential equation. I of t equals ax exponential of minus t over tau plus b. By deriving I, t, and replacing in the differential equation, we find b equals e over rt, and tau equals L over RT. Using the initial conditions, we find A equals minus E on RT. So the solution is I of t equals I0 times 1 minus exponential of minus RT over L times t. So the curve of I of t is of this form. By doing a dimensional analysis, we find that L on RT has the dimensions of a time, so it represents the time constant of the circuit. Tau is the instant when the current is 63% of its maximum value. For the time constant, simply draw the tangent to the UR curve of t at time t equals 0, and the intersection of this tangent with the asymptote to the UR curve of t, the point of intersection whose abscissa is at time t is equal to tau. Alternatively, we can take 0, 63% xi max and the intersection with the UR voltage of t, which will give the same value of tau. Voltage across the resistor. This maximum current can be determined because at the terminals of the assembly, the voltage E is equal to the sum of these two voltages, U, R of t plus UL of T, which is equal to R times I max for the coil, and R times I max for the resistor. And since L times di on dt equals 0 at steady state, we can deduce that, in steady state, I max is equal to E on R plus small r. Voltage across the coil. In steady state, the current becomes constant, so this derivative becomes 0. Hence UL equals small r times I max. So, it behaves like an ohmic conductor of resistance R. And if we can clearly see that the voltage across the coil will decrease to a minimum value, so that UL plus UR is equal to E at each instant. Assuming that the small resistance R of the coil is 0, we can see that UR of T will have an asymptote which has the same value as the generator voltage, and that UL of T will reach the asymptote which becomes 0. We can therefore conclude that there is no resistance and no difference between the asymptote and the generator voltage.